who are these people? All right. Okay, well, happy Monday, happy Valentine's Day, and it's week 7, which is in the quarter system. Week 7 is when the pressure starts to build, and we're trying to keep everything floating and everything. I hope everything's going okay. We spend a lot of time covering floating point arithmetic, and I'm muted, I think. Okay. Oh, now too loud. We covered floating point arithmetic, and we covered a lot of the limitations of just how we represent numbers in the computer. Now, that said, the approximate representations are good enough for most of our applications, right? You know, I don't know how many times in your life where you're like, man, I really needed that 17th decimal of precision. So probably not too often, but yeah, we do have to keep in mind that they are that numbers stored in the computer are approximations. But that lends ourselves to numeric methods where we try to get approximations, approximate solutions to mathematical problems. And so a lot of times there might be some math problem where there's not an exact solution, or it's hard to get some kind of exact solution using algebra or calculus. And in other times there is an exact solution, but computationally it's like really, really, really hard to work out that answer, or might require an unreasonable amount of resources to compute. You know, I mean, just very, very simply, we can say, hey, what's the area of a circle, right? What's the area of a circle? And you learned this back in, I don't know what, 5th grade, 6th grade or something. And you can represent the exact area in terms of pi, but if you wanted a decimal value, of course, it has to be an approximation because you can't get all the infinite number of decimal places of pi. And so we're not going to get that, but an approximation is good enough in our practical day-to-day lives. And so we take advantage of the computer's ability to follow instructions quickly. The computer's really good at doing calculations quickly. It's really good at doing iterative things. It's not good about reasoning about theoretical quantities, right? So anyway, here's an example in statistics that we encounter all the time. So you have the formula for the standard normal PDF, right? It's 1 over root 2 pi e to the negative x squared over 2. And anytime you see e to the negative something squared, that's going to look kind of like a Gaussian distribution. And you know, if you've taken 100b, maybe you're taking 100b right now or something, somewhere along the way, somebody should have told you that this integral is intractable, that there's no closed form solution to the integral to get the CDF of the normal distribution. So there's no closed form solution for the CDF of the normal distribution, but we often need to know what the CDF is. So what do we do? For the computer, we have a function, right? You use qnorm on your computer to get the CDF. And what do we use? We use an approximation. This is there's like a little bit of Fortran code that runs every time you use qnorm, and it calculates an approximation of the CDF, and it's an approximation that's accurate to around 16 decimal places, and that's going to be good enough for us because that's the limit of our floating point arithmetic accuracy anyway. We can't even represent numbers more accurate than 16 decimal places of precision with a floating point number. So if we can get 16 decimal places of precision using an approximate algorithm, we're happy with that. Okay, and so that's what we're doing. We're gonna rewind a little bit and start with some just very, very, very basic numeric methods. And kind of our first class of numeric methods will be root finding methods, and these will be, how do we find the root of a function? The root of a function is basically where the function is equal to 0, or if you just think of drawing the function, it's where the function crosses the x-axis. And how do we figure that out? Well, we're going to look at some root finding methods, and we can do this. So one root finding method that you're already familiar with is the quadratic formula, right? So in your first year of algebra, somewhere 8th grade or whatever, you learned the quadratic formula, where you say, well, okay, here's how we express a quadratic polynomial, degree 2 polynomial, ax squared plus bx plus c. And if you want to find the roots of that, right, you had a few options. One is to kind of like try to factor it out, and you can figure this out, or you could just plug in the coefficients, and you'll get your roots. And before we get into these numeric methods, it's important to note just that if there is an analytic solution and you can find it easily, just use the analytic solution. Don't use a numeric method just for numeric method's sake, except in your upcoming homework 5, I'm going to make you use numeric methods. But on a practical level, if you can avoid using a numeric method and you can get an exact answer, that's going to be preferred. But if it's hard to get the analytic solution, that's when you can consider getting a numeric method, or using a numeric method. Okay, most of my notes are coming straight from this textbook, Introduction to Scientific Programming and Simulation Using R. I believe I have it linked in the syllabus as well, and it should be freely available as long as you're connected to the UCLA network. So while you're on campus here, you should be able to, you can follow the links in the syllabus to download the textbook, or if you're in on-campus housing. If you live off campus, then you have to connect via the VPN, and you can get your stuff. Okay, these are also some good notes from other universities to do this. Okay, let's take a look at our first method here. Okay, you know what? You guys are my last class, so I'll just pass these around. Okay, take the candy and run. Okay. Okay. Don't be shy. Okay. Okay. So fixed point iteration. So the fixed point of a solution is where g of x, if you have a function g of x, the fixed point of this function g of x is where g of x is equal to x. Okay? That is, if you think about the graph, the line y equal to x, just that diagonal line cutting through the Cartesian coordinate plane, it's where g of x crosses that line. And kind of the important fact of this is that if you apply the function to the fixed point, you can keep applying the function over and over and over again, and you're just going to get the same value, right? Because g of x is equal to x, so if I apply g to g of x, that's still x, and if I apply g to g of x, it's always going to be x, okay? And what makes this useful, or why we're interested in this, is that some of these fixed points are known as attractive fixed points, okay? An attractive fixed point is one where if you repeatedly apply g of x to some value x, it's going to get closer and closer and closer. It's going to eventually converge to a value a, okay? So if you do g, you start off at x, you apply g to x, and you get a new value. And then you apply g to that function, and you get a new value. And apply g to that thing, you get a new value. And if you keep going and going and going, that's going to converge to some value a. All right? A little bit more of a formal definition, and don't worry, I won't test you on these formal definitions here. But we're going to say, use this notation g super n of x is what we get when we apply g n times to the value x, okay? and we're going to say there's a fixed point A if there's some interval I such that the value x is going to be within the interval I, okay? And if x is within the interval I, and you apply g n times to this thing, it's also within the interval I, okay? For n greater than 0, right? So as you keep applying g to this thing, it doesn't ever go outside of that interval. And then for all values of x within this thing, as you keep applying g to this value thing, it's going to converge to some point A, okay, as n goes to infinity. So here's an example that I think we're mostly familiar with, is the square root function. The square root function has an attractive fixed point at x equal to 1. And that is, you can start off with any value, and if you apply the square root function, it's just going to get you closer and closer and closer and closer to 1. Okay, so let me pull out a calculator and I'll just demonstrate this. Okay, so okay, so let's do 1 0 0 4. Okay, so here's a big number. All right, we'll take the square root of that. I get 31 million, okay, something around there. Square root of 31 million, 5,600. Square root of that, 74.98. Square root of that, 8.659. Square root of that, 2.94. Square root of that, 1.71, 1.3, 1.14. And I can keep taking the square root, and we're going to get something closer and closer and closer to 1, okay? I can start off with a very, very, very small number, okay? And I can take the square root of this, and I get 4 times 10 to the negative 7, and we get something closer and closer. You know, we get more and more 9s, but we're going to get something closer and closer to 1, okay? And you can just start off with any number you want, right? And you take the square root, and it keeps getting smaller, and eventually, as you keep taking the square root, you get something closer and closer to 1. So we have x equal to 1. That's an attractive fixed point of g of x. And all we have to do is just keep applying the square root function over and over and over again, and it takes us to that fixed point. So fixed point iteration is a method to help figure out a fixed point. And basically, if you've got a fixed point, if there's an attractive fixed point, all you have to do is you take your current value, apply you take your current value x0, you apply g to that value, and that's going to be your value x1. And then you just kind of repeat. If you're at x at time n, you apply g to that thing, you get x at time n plus 1. And you just keep going over and over and over again. And to avoid iterating forever, we're going to say when the difference between your current value, x at time n, and the previous value, x at time n minus 1, when the difference between that, the absolute value of this difference, is less than some tolerance value, so something like 10 to the negative 6 or 10 to the negative 8, some small value, when the difference between the current value and the previous value is less than, say, 1/1,000,000th, we'll say, all right, that's close enough. It hasn't really changed, and we've reached stability, and we'll call it a day there. Okay. I don't know what happened to my picture here, but I'm starting off at 10. Okay, this is 10 on the number line. Here's the function, the square root of x. At 10, I say, what's the square root of 10? The square root of 10 is 3.162. That's right here. So we plug this in, and I follow that to the line y equal to x. And so at 3.162, this is going to be my next value. Okay. So at 3.162, I've traced that down. And I say, okay, at 3.162, what's the square root of 3.162? Okay, that's going to be 1.77. That's this location vertically. This location, we're going to trace that down. What's the square root of 1.77? That's going to be 1.33. All right, I trace that, and I follow that here. And then I say, okay, what's the square root of 1.33? That takes me over to here. And we can see that if I keep going over and over and over again, it's going to get closer and closer and closer to this location where the square root of x crosses y equal to x, and this is going to be at the point 1, x equal to 1. Okay, and so after about 15 more iterations, it gets closer and closer, And after about 15 iterations, we're at 1.0007. So I'm very close to 1. So what we're going to do is, remember the original thing we wanted to do was find the roots of a function. And we're going to say, if we can find fixed points of a function just by applying the function over and over and over again, we can use that to help us find the roots of a function. And so the way we're going to do this is we're going to say, let's say there's some function f. And what we want to do is we want to find the roots of f. And so what we're going to do is we're going to define another function, g, so that when we find the fixed points of g, that location will correspond to a root of f. Okay? So we just want to figure out what g is so that when g of x is equal to x, then f of x is equal to 0. Okay? And there's going to be lots of ways for us to achieve this. Okay? One possibility is all you have to do is you just say g of x is equal to x minus f of x. Right? And this is going to work out because f of x is going to equal 0 if g of x is equal to x. Right? And so that's simple enough. And so that's one way. There's lots of ways for us to figure out some function g of x for this to work out, okay? And what we can do is we can figure out, well, if we define g of x to be this, if we find the fixed points of g of x, that will correspond to the roots of f of x. And we said it's easy to find the fixed points because all we have to do is just repeatedly apply the function g of x over and over again, okay? There's going to be lots of ways to do this, and practically speaking, some of these are going to be better than others. But let's try an example. But before we do, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter C. C as in cat. C as in cat. All right, so let's do this function here. Log of x minus e to the negative x. Log of x minus e to the negative x. And what we want to do is we want to find the roots of this. We want to figure out where this thing is equal to 0. Where this thing is equal to 0. So what we can do is we can kind of rearrange some things. And so we solve for the function in terms of x. So I'm going to add e to the negative x to both sides. I get log of x equal to this. I'm going to exponentiate both sides. So e to the log of x is just x. And e over here, I have e to the negative x. Okay, and I can say, well, let g equal to this thing. And if g of x is equal to x, that's going to be at the same location where f of x is equal to 0. Right? So if g of x, if e to the negative x is equal to x, that's going to be at the same spot where f of x is equal to 0. All right, let's code this up. So I have g of x equal to e to the negative x. And this is fixed point iteration. I'm going to just start off with some arbitrary value. I'm going to just say 10. This is my old value. And we're going to take g, apply g to the old value, and then I'm going to say this is my new value. And then I'm going to start off with 0 iterations. I'm going to make up some tolerance value, arbitrarily selected, 10 to the negative 8, sure. And we're going to just run a while loop. We're going to say while the difference between the new and the old value, while the absolute value of that difference is greater than 10 to the negative 8, do this step. Okay, take the new value, make that the old value. Apply g to this old value, and take the result and make that our new value. Okay, and then we just repeat this over and over again. And then each time we'll increment our iterations by 1. Okay, so this will be it. Now, in general, anytime you have the possibility of running an infinite loop, right? Because this could end up not being always staying true or something. You should have a little line of code as a kind of a fail-safe exit. In terms of if just so you don't run off to infinity, you can just have it stop, right? So you can just say like, if the number of iterations is over some number, just break out of the loop, just so you don't get stuck in an infinite loop. Fortunately for this example, it's not an issue. So So it stops, okay? And we get this value. We get x new 1.3098. 1.3098. I can plug that in to f of x. I say log of x minus e to the negative x. And indeed, we get 9.7 times 10 to the negative 10. So we get a very small value, something very close to 0. And it took me 19 iterations to get there. 19 iterations. So not so bad. We seem to have found a root of this function just by defining another function, g of x, and just applying g of x over and over and over again. And we said, you know, here's a little bit of math that just says, if we assume that the fixed point iteration method does converge, okay, that is to say that we're going to define the next point, x at time n plus 1, to be g of x and n, and we're making this assumption that x and n eventually does converge to a as n goes to infinity, we can show that the value it converges to is going to be a fixed point of g. So we're going to define a as the limit as x at n time n plus 1 as n goes to infinity. This is going to be equal to the limit as g of xn, because this is what we've defined xn plus 1 to be. This is going to be g of the limit of xn, and then, you know, we say, well, this thing, assuming this thing does converge, well, the fixed point it converges to is, or a, the value a that it converges to is indeed a fixed point of g. That a is the fixed point, g of a. So if the fixed point iteration method converges, then it converges to a fixed point. But does fixed point iteration always converge? And unfortunately, the answer is no. Fixed point iteration does not always converge. It relies on the existence of an attractive fixed point. But not all fixed points are attractive. If it is attractive and your initial value is relatively close, and this is just kind of loosely, not even defined, just loosely thrown out there, then the fixed point iteration method will converge. But not all functions have a fixed point, and not all fixed points are attractive. One condition is that if the derivative of g, that is g prime of x at the fixed point, if the derivative of that is less than 1, or the absolute value is less than 1, then it's going to be an attractive fixed point. If the derivative at a is greater than 1, this, even though it's a fixed point, it's a repelling fixed point. And the fixed point iteration method will end up diverging. So let's revisit the same problem, log of x minus e to the negative x. And, you know, I said there's lots of ways for us to write g of x equal to x when f of x equals 0. So one possibility is I can say f of x equals 0 here, and I can add x to both sides. And so now I have x is equal to log of x minus e to the negative x plus x. And we're going to just say, let g of x equal this quantity. Let g of x equal to log of x minus e to the negative x plus x. And we're going to say, well, if g of x equals x, then that means f of x has to equal 0. So that statement is true. The unfortunate thing is that this function g of x does not have an attractive fixed point. And so applying fixed point iteration is not going to get me to the fixed point. So just watch what happens. So we're defining g of x to be this thing, log of x minus e to the negative x plus x, log of x minus e to the negative x plus x. We're going to define g of x to be that function. I'm going to take the same code that I had before. We're going to start off at 10. We're going to say apply g to the old value, make that our new value. And we're going to say keep running as long as the difference between the old and the new is greater than our tolerance, which is 10 to the negative 8. And we're going to do this. And here is my kind of my fail-safe, my iteration limit. And we're going to just say if the iterations goes over 1,000, break out of the loop just so we're not running for infinity. Okay? And we're going to need that because when I run this, the value where I stopped is 7,830. And that could have been a root, but when we plug it in to just check if it is a root, and again, anytime you run some kind of thing where you're looking for a root, always take the value it spits out and plug it back into the function to just see if it's giving you something approximately 0. And if it is, then great. And if it's not, then something went wrong. So when I plug it in, log of this x value minus e to the negative x, I don't get anything close to 0. I get 8.96. Okay, so that's nowhere close to 0. This is not a solution. And if I check the number of iterations that it run, we can see, oh, we hit our iteration limit. We got to 1,001 iterations, and that's why it stopped the loop. It would have kept going forever if I didn't have that iteration limit. All right, let's take a look at the Newton-Raphson method, and let me go ahead and give you your second view quiz answer, which is the letter D. D as in dog is our second view quiz answer. Fixed point iteration is relatively slow. So we did find a fixed point, and we found the root in about 19 iterations. But that's relatively slow, as when you do this, basically the error is usually divided by some constant factor at each iteration. And sometimes it's fine, and sometimes you want something a little bit faster. So one method that is known for very fast convergence is the Newton-Raphson method, and it's very popular. And basically what it's using is we're going to use the tangent line to help us find roots. And so this is how it's going to work. Okay, we're going to say we have some function f. F has a root at a, and we want to try to figure out what this root is. So first of all, f needs to be continuous, and it needs to have a continuous derivative f prime. We're going to say we start off with some initial value x0. And so we say, well, what is the tangent line at x0? Okay? The tangent line at x0 is basically the linear approximation of fx to this thing. That's going to be your value at x0 plus the slope f prime at x0 times x minus x0. Okay? And the reason why this works is if you think back to Taylor expansions for any arbitrary function, the Taylor expansion for any arbitrary function is this. And basically, and the Taylor expansion says, we can write an equivalent function, but in terms of all of these derivatives and stuff, we're basically just throwing away all of these higher order terms, and we're just keeping kind of the first two terms. And so this is going to be a linear approximation to the function. And so this tangent line is going to be a good approximation to f near x0. And so the next point that we're going to use, the next guess x at time 1, is going to be the point where this tangent line crosses the x-axis. So to illustrate, this is we're going to apply Newton-Raphson method to just this very simple function, x squared minus 3. X squared minus 3, I'm going to just plug in x0 at 10. So 10 squared is 100 minus 3. We start off at 97. Here is the tangent line to the parabola here. And it takes me down to this location right here. And I say, okay, what's the next location? 5.15. Okay, I plug that in, and I say, okay, what's the tangent line here? The tangent line here in this red dotted line takes me down to over here, which is 2.86. Okay, and I plug that in, and then I trace that, and that takes me to a tangent line. And then we can see that if I keep going, it's going to get me very close to the solution here. Okay, so if I plug that in, it takes me to 1.95, and then I'm getting a lot closer to the solution x squared to the root of x squared minus 3, which is going to be the square root of 3. All right, so let's talk about how do we figure out what this next value is, right? So here, the next value I used was 5.15. How did I get that? Okay, well, basically, I'm drawing a triangle here, right? I'm drawing a triangle, and we know the length of this side of the triangle. It's just the value of f at x0. This is the value right here is 97. This side has a height of 97, and we want to know what is this length over here. So we say the slope is rise over run. Okay, we want to know what is the run, right? So slope is equal to rise over run. I just rearrange terms, and run is going to equal rise divided by slope. Right? If my rise is 97, my slope is f prime at x0. My slope is going to be, I take f prime 2x, plug in 10, and get 20. I get a slope of 20. So I say this length is going to be 97 divided by 20, 4.85. right? So this length here is 4.85, which is basically f of x0 divided by f prime of x0, 97 divided by 20, 4.85, and then I'm going to just take x0 minus this length here. That's how we get 5.15. So we're going to say my starting point is 10, f at 10 is 97, the slope at 10 is 20, and so the next location is going to be 10 minus 97 over 20, 5.15, and that is to say the next value, x1, is f of x0 divided by f prime at x0. We're going to do x0 minus that quantity there. Okay, and so just more generically, at any time n, the next value n plus at x at time n plus 1, the next value is the current value, x at time n, minus f of x at xn divided by the slope f prime at xn. And so to apply the Newton-Raphson algorithm, wherever you start, you just start off with some initial value x0, and then you're going to calculate the values at the next iterations, x at time n plus 1, using the algorithm, and you're going to stop when this value gets close enough to 0. Okay? When f at xn is close enough to 0, that is to say the absolute value of f of xn is less than or equal to some value e being some tolerance level, some epsilon, maybe 10 to the negative 6, 10 to the negative 8, that's when you'll stop. So let's go ahead and revisit the same equation that we saw earlier. We're going to say let's solve for the root of this function, log of x minus e to the negative x. So I want to take the derivative of this. Derivative of log of x is 1 over x. Derivative of e to the negative x is e to the negative x. But I've got chain rules, so I've got to multiply by a negative 1. So minus e to the negative x becomes plus e to the negative x, and this is going to be my derivative f prime. Okay, so coding this up is pretty straightforward. F of x is log of x minus e to the negative x. And then I have a function f prime, which is going to be 1 over x plus e to the negative x. And I'm going to take f and f prime, and I'm going to use that to figure out my next iteration. So I'm going to just arbitrarily start at x equal to 2. We'll have, I start off with 0 iterations. My tolerance, I'm going to say 10 to the negative 8. And we're going to just say as long as my absolute value of f of x is greater than my tolerance, we'll just keep this running. Okay, and again, I should insert a fail-safe in case the number of iterations goes over 1,000, but just to kind of get it to fit on the slide, I cut that line out. But it works for this example. But we're just, I'm going to just take our current value x, subtract off f of x divided by f prime of x, and that's going to update x accordingly, right? And so I let this run, and it gives me an approximate value of 1.3098. I plug that in, and indeed I get a value close to 0 on the order of 10 to the negative 9, so I'm happy about that. And it only took me 4 iterations to get there. All right, so the Newton-Raphson method converges very quickly. In this case, it only took 4 iterations to get to this value where I'm within 10 to the negative, on the order of 10 to the negative 9, so less than 10 to the negative 8, close to 0. Okay, so this slide, basically, I don't feel like reading all of this, but I'll do it. Basically, this just says that if the Newton-Raphson method converges, the value that it converges to is indeed a root. Okay, so that is to say, x, if we assume, all right, so you got to assume that xn converges to some point a, we can show that a is indeed a root. So we're going to say, we're going to set a equal to xn plus 1 as n goes to infinity. Okay, what is xn plus 1? That's defined as xn minus f of x over f prime of xn. And then, applying the limit through this, we can say, okay, well, the limit as n goes to infinity of xn is going to be a. Limit of n as n goes to infinity f of x is fa, and limit of this is going to be f prime of a. And indeed, well, this is going to be a root. A is going to be a root of f. All right. So assuming that f prime isn't plus or negative infinity, then f of a equals we're going to get 0. Okay, a is going to be a root of f. Okay, but that's assuming the Newton-Raphson method does converge. All right, but does Newton-Raphson method always converge? And the answer, unfortunately, is no. It's not going to always converge. If the function is well behaved, then it'll converge and it'll do it quickly. It converges quadratically, but there are a lot of instances where this thing is not well behaved and doesn't converge. Okay, so here are all sorts of issues that could go wrong where your thing doesn't converge, right? So f prime of x, if this equals 0 for any of your iterations, your thing is going to blow up, okay? Because you're saying the next value is going to be x at time n minus f at xn divided by f prime at xn. And so if f prime at xn is equal to 0, you're trying to divide by 0, and that blows up. It's okay, all right? The derivative f prime is allowed to be 0 at certain locations, but it can't just be, it's not allowed to be 0 at any of your iterative locations, right? So if I go back to here, right, x squared minus 3 is going to have a derivative equal to 0 at x equal to 0, right? So there's no issue with there being a global minimum or local maximum or something where you have the derivative equal to 0. It's just you can't encounter that point along your iterations, right? So you're encountering certain locations as you iterate, and you just can't encounter a spot where the derivative equals 0. Okay, and then you also run into issues. Let's say you didn't exactly hit where x prime is equal to 0, but let's say you got x prime equal to 10 to the negative 5. Okay, so now you're dividing by 1/100th, and so your tangent line is going to be very, very flat. Not totally flat, but close to flat. And so the next iteration is going to be like super far away. It's going to be like at 100,000 or a million or whatever it is. It's going to end up being super far away. So that could also cause issues. Convergence is going to depend on your initial guess. If it's too far from the root, it might not converge, or it might converge to an entirely different root. Sometimes you get into situations where it oscillates back and forth in a cycle, and then it doesn't converge. If your second derivative is infinite or undefined at the root, it can lead into problems. And in some cases, it will still converge, but it might do it very slowly. All right, so here I've got some, here's some examples. All right, so this is one where it behaves nicely, x squared minus 4, the root's right here, and we can run it. Newton's method, you know, it runs and it converges to the root right there. All right, so that's great. All right, so here's a situation where the root is right here, okay? Somewhere around negative 3-ish, okay? But notice right here, there's kind of a spot where it comes close to touching 0, but it doesn't, right? And so the Newton-Raphson method gets a little bit confused and gets stuck there. Eventually, it gets to the root, but watch what happens. So it follows along, it comes here, and it kind of gets, it's like searching for a root around here. Eventually, by luck, it gets kicked out over here, and then it finds the root here, okay? But, you know, when it's over here, it ends up over here, and then ends up on this side, and then ends up over here, ends up over there, and so stuff like that could happen, okay? This one works out. Okay. But here, this one doesn't converge. So notice just what happens here. Let's say we start here. It takes the tangent line and it ends up over here. And watch where this tangent line takes us. Or this takes me to over here. And I calculate the tangent line at this point, and this takes me down to here. And then we calculate the tangent line, and we can see we're going to end up way over here. And then and it falls outside of the window, and the rest of the stuff doesn't get plotted, and it doesn't find the root. Okay, if we started maybe like around here, we would have found it, but with this starting location, we don't find the root. So things like that could happen too. All right, so Newton's method, it's great when it works, but it's not guaranteed to work. And you don't know if it's worked until you try it out, okay? Secant method, how many answers have we given you? 2. Okay, let me go ahead and give you your third answer. Third answer is A. A as an apple. A as an apple is your third view quiz answer. All right, the secant method is kind of an alternative. It's like Newton-Raphson method, but one disadvantage of the Newton-Raphson method is that we have to figure out the derivative, f prime, right? And so depending on the function, figuring out the derivative of the function could be something hard for us to do, okay? So we've got to, for Newton-Raphson method, you got to figure out the derivative. And so we have ways around this, and I can talk about how we can approximate the derivative numerically. But the secant method just says, you know what, we don't even need to worry about figuring out the derivative. What we're going to do is we're going to draw a secant line instead. So instead of having one point and a tangent line, I'm going to have 2 points, and I'm going to connect them with a straight line, a secant line. And that's going to be my approximation. Okay, so we need 2 initial guesses for secant method. You need an x0 and an x1. And it doesn't matter if x0 is the bigger one or a smaller, or if one's bigger than the root or one's smaller, okay? All we're doing is we're going to just try to connect these points. Okay, so we look at x0 and f of x0, x1 and f of x1, and we draw a line that connects them. That's going to be our secant line. All right, so here, rather than drawing a tangent line, so this is the same equation, x squared minus 3, my initial point is going to be x0 at 10, and my arbitrary second starting point is going to be x1 equal to 8. And rather than drawing a tangent line at x equal to 10, I'm drawing a line that connects this dot to this dot. I'm drawing a secant line that connects these 2 things. And I trace that secant line down to the x-axis, and this is going to be my next location, right? And so the next location, I don't know, this is like 4 point something. I'm going to plug that in, and I'm going to draw a secant line that connects from 8 to whatever this is, 4 point something. Okay, and I trace that, and that takes me down to here. And so the next iteration, I take this location and this location, and I trace the secant line. So it ends up looking like Newton-Raphson method, but the tangent line, we don't calculate the tangent line. I'm just using 2 points, connecting them with a straight line, and tracing them down to the x-axis. So how do we figure out the next value? Well, we start off with our 2 initial starting points, 10 and 8, and I calculate their points, 97 and 61. And we say, okay, well, what is the change in y divided by the change in x? All right, and that's how I get my slope. Okay, so the change in y is going to be 61 minus 97. The change in x is 8 minus 10. Right? So I have a slope of 18. So this line that I draw here has a slope of 18, which is a little different from the original. The tangent line has a slope of 20. This one has a slightly shallower slope, as a slope of 18. Okay, and so we say, all right, so in point slope form, what is the equation of the line that passes through that? We're going to say y minus f of x1 times the slope 18 minus x1. So we plug in kind of the point, 861. And this is the equation of that line, and we want to figure out where this line crosses the line 0, right? Where y equals 0. And so we plug that in, and we're going to say, okay, let's plug in 0 for y, solve for x. We'll get 8 minus 61 times 1 over 18, and the next value is going to be 4.611. Right, so just kind of solving for that. And so just more generally, when you find the slope of the secant line, it's going to be the change in y at these 2 locations, x0 and x1, divided by the change in x between x0 and x1. And then if you plug this in into point slope form, you get y minus f at x1 times m times x minus x1. And plugging in this thing for the slope, all right? And then we're going to say, all right, let's find where this is equal to, where we're going to find the location x2 where y is equal to 0. We plug that in, and we're going to solve for where x2 is going to be. and that's going to be x1 minus f of x1 times, basically, this is 1 over the slope, 1 over slope of the secant line. Right? And this is very much like, if you think of Newton-Raphson equation, your next iteration is your current iteration minus f at the current iteration divided by the slope at the current iteration. And basically, here we just have an approximation of the slope using the secant line. And so that's what we have, okay? So this is the secant method in general, and I'll leave it to you in a homework exercise to kind of code this up to use the secant method. So I know you guys are still working on homework 4. I mean, some of you are done, and you've already submitted your homework 4, but others of you are still working on it, and that's due Wednesday. But I'll go ahead and I'll post homework 5 if you're ready to tackle that. Otherwise, it'll be up there waiting for you after you finish homework 4, okay? And so this is the algorithm kind of written out, and you'll just keep running until f of xn reaches something that's close to 0, less than some tolerance level e. All right, and similarly to the Newton-Raphson method, secant method is not guaranteed to converge. A lot of times it converges, but not always. And the kind of the pros and cons of secant method versus Newton-Raphson. Pro is you don't need to calculate, or you don't need to know how to solve for the derivative. The con is you need 2 starting locations, and sometimes, your iterations require a little bit more calculations and stuff, but it could work. Okay, we're going to run out of time, so I'll cover bisection method later, and then we'll also talk about approximating derivatives numerically. But we'll end here for today. Have a great, happy Valentine's Day. Have a great rest of your day, and we'll see you guys on Wednesday.